Hello again. My name is Timur Doumler. I'm C++ developer advocate at JetBrains, and this is the third of my 3 talks in a row talk marathon at NDC TechTown. Thank you very much for coming, especially those of you who have stuck around in this room. Really appreciate that. So this is a talk called C++ Lambda Idioms, and it's about lambdas in C++. And I'm going to try and do kind of 2 things here in this talk. On the one hand, kind of dig a little bit deeper into how lambdas actually work in C++ and what are some kind of the traps that you can fall into when using them, or things you should keep in mind, or kind of maybe some surprising properties as well. And then the other thing that I want to do is to talk about a few idioms or patterns that I have seen people use when programming with lambdas in C++ that I kind of see popping up and that I think might be interesting or useful, it's probably interesting to know about. And I'm also going to kind of look at how lambdas kind of evolve throughout the different versions of the C++ standard. And my ambitious goal is that every one of you should learn something about lambdas today that you have not known before. So let's see if I achieve this very ambitious goal. Let's start. Lambdas exist in C++ since C++ 11. Here's a very simple example. You have struct person, you have some vector of people, and you want to do something with this vector. You use a std algorithm, like for example, you want to sort it. A lot of std algorithms have functions that you can pass in as parameters. For example, sort accepts a predicate that tells it how to sort things, what the comparison operator function is. And so you can use the default or you can pass in your own. In C++ 98, we had to either pass a raw function pointer or pass like a handwritten struct with a call operator, or there were some like ugly macro-based solutions like boost lambda, if anybody remembers that. Since C++ 11, we have lambdas, and this is one of the many use cases for them. And I'm going to assume that you're familiar with this basic syntax. I'm not going to explain lambdas from scratch, so I hope you know what it means when you write square bracket, which is the lambda introducer, and then you write a lambda expression. But I want to dig a little bit deeper into what actually happens under the hood. So the C++ standard, this is a screenshot from the C++ standard, actually spells out very exactly what happens if you write a lambda expression. You write a lambda expression, it's going to create under the hood a so-called closure type, which is a class that has a public inline function call operator, right? So if you imagine that at the top is the code you wrote, and at the bottom is some approximation of what the compiler generates under the hood, then it's going to be something like this. You write a lambda expression here, and what you get is a closure type, which is a class type. The name of that type is something you cannot name, is some internal string that the compiler generates every time you write a new lambda expression, and you cannot name that type. I wrote __ lambda something here. In practice, it's probably going to be something longer, involving maybe the file name or something like that, something unique. And then it's going to create a temporary instance of that type. And that's what you get. And then you can do with it whatever you want. You can assign it to another variable or whatever. A few things that are worth keeping in mind. This inline call operator here. Oh, and of course, the body of the inline call operator is going to be the body of the lambda expression that you wrote. Right? That should be pretty obvious. A few things to keep in mind. This operator by default is going to be const. So that's one of the cases where C++ actually got the defaults right. It's const by default. If you want it to not be const, you have to explicitly write mutable. Otherwise, it's going to be const by default. The compiler is going to deduce the return type for you automatically. So in this case, it's going to return a bool. But of course, you can also overwrite that. You can explicitly write the return type with the trailing return type. It's not no except by default. If you want it to be no except that function, you need to write that. Yeah, that's pretty much it. This is kind of what you get. You get a little bit more than that. In C++ 11, the standard also says that a closure type has a deleted default constructor and a deleted assignment operator, so you cannot default construct them and you cannot assign them. So the only instance of the closure type is going to be the one instance that the compiler has generated for you as the result of you writing that Lambda expression. And then the other really cool feature that you get kind of out of the box is that if your Lambda has no state, if you don't have any capture, if the square brackets at the beginning are empty, it's going to generate an implicit conversion operator to function pointer. So Lambdas without captures are implicitly convertible to function pointers, which is really cool if you have some kind of legacy API, typically like a C library or something, which takes a pointer to a raw function. You can just pass in a Lambda expression as long as there's nothing in the square brackets there. It just works, right? As long as this is empty. The standard again spells pretty precisely what that is. It's a conversion function to pointer to function. The type of that pointer to function is matching the function signature of the Lambda that you wrote, and then you get this inline conversion operator here. So that's what the compiler also generates for you, provided that you have no captures. And now we already come to the first Lambda idiom of the day, which is the unary plus trick. So as I already said, you get implicit conversion to function pointer here, right? So that works. But what if we want to explicitly convert to a function pointer? So for example, here, like this is kind of a bit of a contrived example, but it's kind of, I think it's kind of cool. So you have this variable here, f pointer, which is the Lambda, and this is now of type Lambda something, something, something. But what if you want f pointer to actually be a function pointer? Like here, like you're asserting that it's the same type as a function pointer. This obviously will error out because it's not the same type. What if you want it to be the same type? Well, you can statically cast it to function pointer type, which is a bit long. But you can also just write it like that. You can just put a plus in the front, and that's gonna do the same thing. And it's kind of cool to try and understand what happens here. The unary plus operator is not defined for Lambda expressions, but it is defined for pointers, including for function pointers. So if you write this, the compiler is gonna implicitly convert your Lambda to a function pointer, and then it's going to apply the unary plus operator to that function pointer. And the unary plus operator applied to a pointer does exactly nothing. So what this is just a shorthand for a static cast to function pointer. So I think that's a pretty cool hack. But let's talk about Lambdas that do actually capture something, because that comes up quite a lot. Again, I'm not going to explain everything to you. I'm assuming that you have some basic knowledge of how Lambda captures work. You can capture stuff by value using the equal sign. You can capture stuff by reference. You can capture things explicitly, implicitly. You can do some kind of mixture of capturing by value and by reference. There's syntax for all of this. If you capture stuff by value, like here, what the compiler generates for you is something like this. So for every entity you're capturing by value, in this case, it's this int I and int j, it's going to generate a private non-static class member for you. The name of that class member, though, is again something you cannot name. That's why I wrote like underscore underscore I there. You can't actually write lambda.i. That's not going to work. You cannot name these members, but you can use the identifier that you caught. Like you can use the I and the j, and those names are just going to automatically refer to these new private members that the compiler has generated for you, and it's going to initialize them automatically with whatever value those variables had at the point where you wrote the Lambda expression. And so, the standard kind of says what happens here. It says that for each entity captured by copy, an unnamed non-static data member is declared, which is what I just showed. It also says that the declaration order of these members is undefined, so you cannot rely on them being declared in the same order as the variables that you're capturing. If you're capturing stuff by reference, it's kind of the same thing. You again get something like private members of reference type that you cannot name, and they're going to be initialized correctly and everything, and you can just, that's what you're effectively using. However, in this case, the compiler has a little bit more implementation freedom. Actually, in fact, the standard says if you capture stuff by reference, if it's unspecified whether additional unnamed non-static data members are declared, and if so, how many of them there are. And that is just to give the compiler a little bit more freedom to optimize things. For example, if you're capturing two variables by reference, but you only ever use one of them at a time, the compiler can use one pointer to refer to like first one and then the other under the hood, instead of having to store two pointers. So this is to allow optimizations like this. So this is interesting. Again, reminder, the inline call operator of a closure type is const by default. So if you are capturing stuff by reference, you can use the reference to modify the value. However, if you capture stuff by value, you cannot mutate those variables inside the Lambda because it's const. You cannot mutate a data member of a class in a const function. You can also capture this, and then you get to just use members and member functions of that object inside the Lambda expression. What the compiler is going to do under the hood, it's going to capture this pointer again as a private member, and then it's going to translate calls that mention members and member functions into an access through this pointer that has been captured. And actually, this is kind of a little bit more complicated. There's different ways you can capture this by value or by pointer, and like the rules, how exactly you spell that, have also changed throughout the C++ standard. So I'm not gonna. There's a little bit of a rabbit hole. I'm not gonna go into capturing this here. But if you need that, you run into a problem, you can look up these rules. They're all on CPP reference. Yeah, I mentioned that this is going to be translated to an access through this pointer. There is, however, some other gotchas with Lambda captures that I think it's worth pointing out because it's not evident. And certainly for me, when I stumbled upon them, I was like, what the hell is going on here? That was not obvious to me at all. So I think it's worth talking about that a little bit. One really important thing of Lambda captures is that you're only ever capturing local variables. If something is not a local variable, a Lambda is not going to capture it. In particular, if you have a static variable, static object like here. Static objects are not local objects. Even if they're only visible locally, they have static storage durations that aren't actually local. So you're not capturing them. So here you have a static int, and then maybe you think you're capturing it by value, but it's not a local variable, so you're not capturing it by value. So if you actually increment that integer, you're actually incrementing the int I on the outside. And you're modifying that inside the Lambda. And this function is going to return 43. Okay. And in fact, you're not capturing anything, so you can actually leave that empty and it's still going to work and do exactly the same thing because it's not a local variable. You're not capturing it, you're just accessing it because it's just there, right? It's the same with global variables, which I hope you have not that many of in your code. Exactly the same thing. You're not capturing global variables. That's not a thing. You just use them. So again, this Lambda will modify the outside I. It's a little bit more tricky than that, actually, because not only do you not capture local variables, but also Lambdas only capture things that are ODR used inside the Lambda. And here's an interesting example. If you have a constexpr variable, it means that it's a variable of which the value is known at compile time. Okay? And using that value is not an ODR use of that variable because it's just a constant at compile time. So using the value of a constexpr object is not an ODR use of the variable. And therefore, you don't have to capture it. So this code is going to compile, even though those brackets are empty, you can still use the I inside because you're not ODR using it. So you don't have to capture it. However, if you take the address of that variable, that is an ODR use. So that is not going to compile because you're not capturing it. And now you have to write the capture here. And that works. It gets even more tricky than that because const variables of integer type are implicitly constexpr. So if you have a const int and you didn't write constexpr, it's still constexpr. And you still are not capturing it. So this code will work. However, if you make that a float, floating point types are not integer types, so they're not implicitly constexpr, and so that is not going to compile. Okay, so that's worth keeping in mind. All right, enough about captures. We come to our second Lambda idiom, which I think is the most important. I'm going to talk about the most widespread. I think the one that I have already seen being used quite a lot, like several years ago. I think it's a pretty established idiom, so probably many of you have already seen this, but I think it's so important that we should really talk about this because I think every C++ developer should be aware of those. Immediately invoked function expressions, or some people also call them immediately invoked lambdas. What's that? Now we kind of know what the compiler generates under the hood if you write a lambda expression. it's generating you this closure type, and it's going to create a temporary instance of that type, right? And so you can assign that to a variable, which is what we have been doing before, but you can also just call it right there, right? You don't have to assign it to a variable. You can just take this temporary object of closure type, and you can just immediately call it, and then that's it. And then it's just, because it's a temporary, it's just going to make poof and go out of scope, and that's it. And that's totally fine. So what's happening here is you basically just print hello world. This is just a weird way of writing the cout hello world, right? You might think this is maybe not that useful, but actually it's super useful. Here's one case where it's super useful. Initializing objects. Imagine you have an object and you want to initialize it, and it has some kind of complex initialization code. It's not just you assign a value to it, but you need to write some code in order to initialize it with the value, right? You have some condition in there. Maybe there's a little bit more going on. And so the way a lot of people are writing this is you first declare the object, and then you kind of figure out what the value is, and you assign the value to that object, which isn't great, because if you declare it, you're not initializing it, so potentially there's some uninitialized values there. Like if in between you access it, it's undefined behavior. You kind of have this two-step initialization. It's not great. It's not a good way to write this. And it might not even compile if foo doesn't have a default constructor. Then it's just not going to work. And it's also not going to work if foo is const. Then you cannot assign to a const object. Now, you can do this in Java. In Java, instead of const, has the final keyword, which basically just means you can assign to this object exactly once. So in Java, this would work. But in C++, it means you can only assign it at the point where you declare it. And so this two-step initialization is not going to work for a const object. How can we work around this? Well, we can maybe, if it's something relatively simple, like here, we can write a ternary expression that's going to work in this case. But if you have something more complicated, the ternary expression is going to get really, really ugly really quickly. What else can we do? We can factor the initialization out into a separate function. And then you can assign the return value of that function. This is going to work, but now you're kind of separating your logic, right? You have your code spread over different parts in your file, or maybe even multiple files, so it becomes kind of more difficult to reason about. Also, if the initialization depends on some local variable, now you have to pass that variable as an argument to that function, so everything becomes more complicated. It's just not good. And immediately invoked lambdas solve this problem, because what you can do is you can declare the object and then write a lambda expression that's going to return the value that you want to assign to, and then you can immediately invoke that lambda, which is the paren at the end. So it's going to return that value, and you're going to immediately assign it to the object. And now you can make it const, and it works. So this is the idiom. I think it's really, really cool. It not only works for this kind of simple initialization, it also works for perfect forwarding stuff like mplace back into a vector, or like make shared, make unique, whatever. You can just stick a lambda in there and immediately invoke it. Now, some people say it's not very readable because it's very easy to overlook these parens at the end. And like it might look like you're passing the lambda as a parameter, whereas actually you're evaluating the lambda in there and then you're passing the return value, right? So it's easy to overlook. And so one way we can mitigate this is, instead of writing paren at the end, is we can write std_invoke at the beginning, which is a library function which literally just takes a function and calls it. That's all it does. But it's kind of spelled out, and it's in the beginning rather than in the end. So it's like a little bit more visible that, yes, I'm calling it here, right? So it's a matter of code style. You don't have to do this. Maybe it's useful sometimes to make it a bit more obvious what's going on here. So there's actually another idiom which kind of uses these immediately invoked lambdas. So this is just another kind of example of the cool stuff that you can do with immediately invoked lambdas. This one I've learned from Daisy Holman in her fantastic talk, What You Can Learn from Being Too Cute, from last year's CPPCon. And what we're trying to do here is we are trying to write some code that will be executed exactly once. So this is actually quite useful. Imagine you have some kind of struct and you have a constructor, and then there is some code here and you want to only call this once. This actually comes up. I have a library where I basically need to check. I have like a thingy, and I need to check whether the CPU I'm running this on supports a particular CPU instruction. People who have been to the Atomic Shared Pointer talk couple of hours ago probably know what this is about. So you need to check. There's a way to work around this issue that I was talking about by actually checking at runtime on Linux. Does the CPU support a double with compare and swap instruction? And so you need to do that runtime check, but you only need to do it once, the first time you use the thingy, and you don't have to ever do this again. So you don't want to do it in every call of the constructor. You don't want to do it all over again every time you construct an X. You just want to do it exactly once. So if we create, I don't know, 3 of these, you still want this called once to be printed only once. How can we achieve this? We can wrap this into a Lambda, because Lambdas solve everything. Then we need to return some value from this Lambda. It doesn't really matter what we return. We just need to return something. And then we can immediately invoke that Lambda and return that value, which means this code is going to be evaluated. And then we can assign it to a static local object, right? And that's going to do the trick here. People who have read Scott Myers and know about the Myers singleton probably know what's going on here. If you have a static object, there's a guarantee in the standard that static objects are going to be initialized only once, right? So this Lambda is going to be evaluated exactly once whenever the first time is that you call one of those constructors. And not only is it guaranteed to be called exactly once, but static initialization of static objects in standard C++ have another property, since C++ 11, I should say, is that it's also thread safe. Like, it's guaranteed that installation will happen only once on exactly one thread, and there's not going to be a race condition. So the compiler is going to insert mutexes in there as needed to make sure that this is the case. You don't have to worry about this. So actually, you can create these instances of X on multiple threads at the same time, even. And you still get the guarantee that this code is exactly going to be executed once, and there's not going to be a race condition. So I think that's a really cool kind of creative way to use Lambdas. In fact, there is a function in the standard library called std_call_once, which is doing exactly this. However, Daisy found in her code that if you just do it by hand like this, it's going to be a lot faster than std_call_once, which for some reason is not performing very well, at least on some standard library implementations. I don't know why. Maybe they're going to fix that, but I think this is a really cool trick. All right, we're done with C++ 11. Let's move on to C++ 14. In C++ 14, we got a really big feature, which is generic lambdas. So now, if you write a lambda expression, for example, here, instead of a vector, I have a map, and now again, I want to do some std algorithm and pass some predicate. I don't have to write out the parameter type of the lambda. I can just write auto, and then the parameter type is going to be deduced automatically for me. And that's really great in cases like this, where what's the element type of std map? Hint, it's not std pair of int and std string. Probably not everybody can spell out the correct element type on the first try. You don't have to. You can just write auto, and the compiler is going to deduce that for you. What's actually happening here under the hood? So if you write a generic lambda expression like this one, where you have an auto parameter, again, on the left is your code, and on the right is some approximation of what the compiler generates under the hood, and it's something like this, where again, you have this closure type that's going to be generated with some kind of weird name that you cannot name. And you still have the inline. Actually, I think I forgot the inline here. Oh no, it's a template, so it's implicitly inline, right? Yeah, okay, so we're good. So it's creating your inline call operator as before, but this is now a template, a function template. And this is really important. Actually, for a while, I thought that the lambda, the closure type itself, would be a template. That's wrong. The closure type is not a template. The call operator is a function template. Right? This is really, really important. This is what actually happens here. And then, yeah, the type of the argument is going to be deduced from what you actually call it with, using the usual rules of function template argument deduction that we always had in C++. So there's no magic going on there. And then if your square brackets are empty, if you're not capturing anything, you don't have any state, then you still also get this implicit conversion to function pointer, this operator. You still get that as well, but now that conversion operator is also a template. And that's really cool because that actually works. Like if you have your legacy C API, you can pass in a generic lambda, And it's still going to work. It's still going to figure out, oh, you're calling it with 7, which is an int. So we want to instantiate the int version of that, right? So generic lambdas still do work with these like function pointer APIs, which is really cool. However, the plus trick does not work anymore, because if you just write plus generic lambda, compiler's not going to know what function pointer type you want to convert it to, right? Because the call operator is a function template, it also works with forwarding references. So here in this case, this is a forwarding reference, autoref. So you can use it with, you know, emplace, back, make, shared, whatever. Like it works. You can forward it then to other types. I actually realized I should probably write emplace back instead of push back. That would probably be better. I'm gonna fix that. Yeah, you can see here, this is what the compiler generates. You can see here very obviously that this is a forwarding reference now. It also supports variadic templates, right? So you can write variadic lambdas, which is really cool. And you can write really cool stuff like this kind of thing. Makes it really easy to take lambdas and pass them as arguments to other lambdas. So you can use this like higher level functional programming stuff if you're into that. So you can write a lambda which is taking another lambda as an argument and it's returning another lambda which calls the first lambda twice. And you know, this, you can do lots of really fun stuff with this if you're into functional programming. It just makes it so easy to write this. And we come with to the next idiom, which has to do with variable lambdas. And this is actually something that Björn invented, Björn Fowler, who is here at this conference. Not sure if he's in the room. Yes, Björn, here you are. So this is something I got from Björn. I think he posted it on Twitter. So remember that if you write a generic lambda, then the template is on the call operator. It's on the call operator. So the lambda itself isn't a template. The call operator is. But what if we could make the lambda itself also a template? So this comes back to a thread on Twitter, I think about 2 months ago, where I posted on Twitter, hey, I'm preparing this talk about lambdas. I found this cool trick. What cool tricks have you found? And then Björn posted this. You can make a lambda a variable template and access the template parameter in it. And wrote this little snippet of code here. I was like, all right, I don't understand this, but this is super interesting. What's going on here? And so yeah, I kind of went ahead and took this apart a little bit. So you have a variable template here and you assign a generic lambda to it. And then you can call that lambda and you can specify the template parameter here, right? The template parameter of the variable. And what actually happens under the hood? So this is again some rough approximation of what the compiler kind of does with it. And I think this is really, really cool. So you have two sets of template parameters here. One is the template parameter of the variable template that you wrote. So that's effectively the template parameter of the lambda itself. And that's, in this case, it's a cast, so it's like the type you're casting to. And that is going to be a template parameter of the actual lambda. And then we have another set of template parameters, which is templates of the generic lambda, which are the template parameters of the call operator. And that's a different set of template parameters, right? So what we can do is we can take the template parameters and separate them into two groups. One is the one that you specify when you write the lambda, and the other one is the one that's going to be deduced when you call it, right? And we can separate those into two different things. And then I was like, okay, this is cool, but is there actually a use case for this? And then I messaged Björn, and thank you, Björn, for replying. You actually came up with kind of a really cool example, which I'm going to reproduce here. So this is what Björn sent me. And he actually said, oh, actually, I used this once in production code. I think probably it was not this code, it was something else, but this is the example that he came up with, which I think is cool. So what's going on here? We have a struct time, which is storing a time point somehow. It's not really important, like how, like in this case, it's a variant, and for some reason you can store it as milliseconds or as nanoseconds. You can choose either representation. It's a variant. And then it has this member function convert. It takes the converter and then it converts this time point to something else by calling std_visit on it. right? So std_visit is going to call this converter either on the millisecond version or in the nanosecond version, depending on kind of what's applicable here. And that actually doesn't compile. So here so what we do is, okay, our converter is, we want to convert it to microseconds. So we say, okay, std chrono duration cost microseconds, and we're going to pass that in as our converter, and we get a compiler error. Can anybody tell me why this is not going to compile? Right. So std chrono duration cost is a function template. And what you're trying to do is you're trying to pass it as essentially as a function pointer. However, you cannot have a pointer to a function template. You have to fully specify all the template parameters to turn it into a normal function. However, we didn't do that here. We only specified the first template argument. Chrono duration cost actually has 3 template arguments. If you look in the definition, it has one template parameter, which is the duration you're converting to, and that's typically the one that you specify by hand. And then it has 2 more, the rep and the period, which are typically just deduced automatically from the arguments. So you don't typically spell these 2. But they're there. So if you want to pass this as a function to another function, you need to specify all of them. But you can't do that because you don't know, which rep and period you want to call this with, right? You don't know that. The call set is going to do that. So this doesn't work. But here we can actually use the variable lambda pattern. So we can make this a variable template, and we can say, okay, so this first template parameter, the one that we want to specify, like the duration that we want to cast it to, that's going to be the template parameter of the lambda itself. So that's the thing we're going to write when we call it, right? So template item t, and t now is going to be it's going to be this microseconds here. So the microseconds here, we specify those. Those are the template parameters of the lambda itself, right? And then the other 2 template parameters, well, those are now going to be template parameters of the generic lambda. So those are going to be deduced from the O2D. We don't write that. We're going to let the call site, which is going to be somewhere inside the convert visit there. It's going to be somewhere inside the std visit. It's going to actually call this function. At that point, it will actually deduce the template parameters there. So you can kind of separate out the template parameters into like one group, which is the one that you want to specify by hand, and another group which you want to be deduced automatically by the usual kind of generic lambda mechanism. And you can kind of separate them out like this. So again, this is the template parameter of the lambda itself. This is the one you write. And these 2 template parameters, it's going to be deduced. These 2 template parameters of duration cost, of which there are 2, they're both going to be deduced from the O2D, which is our generic lambda. Right. So that's the pattern. I think it's cool. It's probably not very common. It's probably quite rare that you stumble upon this, but if you do, it might be a handy tool. Right. Let's talk about another feature that we got in C++14, which is init capture. Init capture is really cool. In C++11, there was no way to capture a move-only variable, like unique pointer, for example. In C++14, you can do that by writing it like this. This is an init capture. You kind of declare a new variable inside the capture, and you assign to it, and you can do a std move in there. You can use the same name as the variable you're assigning. You don't have to. You can also give it a different name. It doesn't really matter. What happens under the hood? Again, this is the code that compiler kind of generates under the hood. It's going to create a private non-static data member for your variable. It's going to deduce the right type from the initializer. So in this case, it's a unique pointer of widget. So you get a implicit kind of hidden private member in your closure type, which is a unique pointer of widget. And then it's going to be initialized appropriately with the std move that you wrote. Okay, so this is what's going to happen if you write a init capture. And this is really cool. And here's another idiom, which I think is one of those really important ones that you really should be aware of. And this comes from a book by Bartłomiej Filipek called C++ Lambda Story. It's really, really cool. You can get that online. It goes into a lot more detail on some of the stuff than I can do this in my talk here. So very much recommend you check out this book. So I got permission from Bartłomiej to reproduce one of his code examples from the book in this talk. And And this is the code example. The details don't really matter. We have a vector of strings, and then we do something with it. We do a std algorithm here, and we do a find if. And then we have the string here, some constant string. And then we capture that string by reference in our Lambda. And then we do something with it. In particular, here we are appending another string to it. So that's going to create a new string instance that's potentially memory allocation. And because we are passing this Lambda into find if, it's going to call this in a loop. Right? So this Lambda is going to be called potentially like 1,000 times. And every single time it's going to do this computation and create a new string object and potentially allocate memory. And every single time the result is going to be the same. So we're just wasting CPU cycles. And what we can do is we can take this computation and move it into the init capture. And now it's only going to happen once. And your code is going to run faster. And we're creating this new variable here, stir, and then we can just use that thing inside our Lambda. And that's the kind of init capture optimization pattern. So I think that's really cool as well. Right. That's C++ 14. Let's move on to C++ 17. In C++ 17, we got, again, lots of new features. Since C++ 17, Lambdas can be constexpr. That's really cool because now you can use them for compile time metaprogramming. You can, for example, take a Lambda and use the result of a Lambda as a non-type template parameter and do things like that. This is a lot of fun. You also have another feature in C++ 17, which is called class template argument deduction, or CTAD. One of my favorite features. It's what it allows you to do is, if you have a class template, you don't have to actually spell out the template arguments anymore. You can just leave them out. For example, std vector. You don't have to write std vector of int. You can just write std vector, and it's going to deduce the int from the initializer. So in here you have an initializer list of ints, and it's going to just figure out from that it's a vector of int. Now that doesn't really have anything to do with Lambdas in itself. But it allows another really, really cool pattern, which I call the Lambda overload set, which again, has been around for a couple of years. You can find it on CPP reference, so I think it's very useful. It's very, very useful to be aware of that. The idea here is that we want to create an object which represents an overload set. So we have a callable object, and it has a bunch of overloads. Like, I don't know, one for int and one for float. And when we call that, it's going to call the correct overload under the hood. And we want to pass it a bunch of lambdas, and it's going to take that lambdas and put them into an overload set. We can do that by inheriting from those lambdas and using the call operator of the lambda. Inheriting from lambdas sounds weird. Well, a lambda it's a closure type, right? We saw what type the compiler generates for you. It's a class. If it's a class, you can inherit from it. Of course, you cannot name the type, but what you can do is you can write a variety class template, which is takes a bunch of types and just inherits from all of them. And then it's just using the call operator of those types, right? So it has a bunch of base classes, and it's just going to inherit the call operator from all of its base classes. Is that clear what's going on here? Okay, cool. And now what we can do, note that this class is an aggregate. It's an aggregate class because it has no user-defined constructors or anything like this. It has no private members. The only thing it has, it's a bunch of base classes. So it's going to be an aggregate, and its base classes are going to be its aggregate elements. Therefore, you can initialize it using aggregate initialization. So let's do that. You can initialize an overload. And I'm using the curly brackets here. And we're going to give it a bunch of lambdas, and those are going to be the base classes. And in C++ 17, I have to write the deduction guide for this, which since C++ 20, we don't need anymore because we have automatic CTAD for aggregates in C++ 20. So this code in C++ 20 is just going to work. And once you have this f, it's really cool. If you call it with an int, it's going to do the int thingy. And if you call it with a float, it's going to do the float thingy. So it behaves like an overload set. You obviously can also, give it more lambdas. You can also give it other callable objects. They don't have to be lambdas, but it's just particularly cool if you use lambdas because you can write the whole thing in one line. And it's also particularly cool if you use it with std variant. For example, if you have a std variant, which can be either an int or a float, You can just call std_visit and give it the f, and then it's going to call the right thing depending on what type the variant currently holds, right? So if the variant is a float, it's going to print float thingy, and if the variant happens to at this time hold an int, it's going to print the int thingy. So I think that's a really, really cool pattern. Okay, C++ 17. C++ 20. C++ 20, again, lots of cool new stuff. Since C++ 20, Lambdas can capture structured bindings. Lambdas can capture parameter packs, which is pretty cool. Lambdas can be const_eval, which means if you have a constexpr lambda, you can run it, you can call it at compile time. If you have a const_eval lambda, you can only call it at compile time, right? It's called an immediate function. It's a function you can only call during compile time constant evaluation. So if you call a const_eval lambda with a compile time constant like 5, that's okay. If you call it with something runtime, a runtime thing like a variable x, it's going to give you an error. No, this is not a constant expression. I cannot evaluate x at compile time. So this is really cool again for metaprogramming. And then another feature we have in C++ 20 is templated lambdas. So if you have a generic lambda, we can now actually explicitly specify the type name, the template parameter list for each generic lambda. And in this case, it's maybe unnecessary, but if you have something more complex, maybe you want to write a requires clause for this lambda. You really need to be able to name this type. And previously, if you write it like this, it's not possible. But like this, you can actually name the t, and you can do metaprogramming with it, like inside the lambda, which is kind of cool. And then the other thing that we have inside C++ 20, which is really cool, is lambdas are now allowed in unevaluated contexts. For example, decal type. You can write decal type lambda expression. And if you don't have any captures, if your lambda is stateless, you can now default construct it and assign it. And remember, that was forbidden before. That rule is gone. If you don't have captures, you can now default construct and assign lambdas, which means you can do something that we were never be able to do before. You can actually have a lambda as a non-static data member of a class. There was no way to write this before. Like you could template on whatever class, but you could not make lambda explicitly a member, because you would have to write it like this: auto f equals lambda expression, but you cannot declare a member of a class with auto. That's not going to compile. Since C++ 20, you can write it like this. You can say decal type of the lambda expression, and that's going to generate the closure type for you. And then you're going to say, okay, just default construct one of those, and that's going to be your lambda. You might think, okay, why would I ever write this? But actually, this comes up a lot. In fact, it comes up every time you have a template where it has a function. It expects a function as a template parameter, and that is all over the standard library. For example, unique pointer. The first template parameter is the element type. The second parameter is a custom deleter. And previously, you had to give the unique pointer a custom deleter at runtime when you construct it. Now you can just put it in the template parameter list. You can just say, okay, this is my deleter. You write a lambda, and then you say decal type of that, and that's going to be my my custom deleter. And now it's baked into the type. You can make a type def, and you can just default construct those, and they're all gonna have that deleter. Same with std_set. Std_set has a second template parameter, which is the less than comparison function that's going to use to sort the elements. Again, you can say decal type of my lambda and give it a custom comparison operator. And again, you don't have to do it at runtime. You can just bake it into the type and just make it very easy to use this. Actually, it's worth digging a little bit deeper into how this works, because I found this to be a little bit confusing. Like the important rule to keep in mind is that every new lambda expression generates a new closure type. This is something that confused me in the beginning, and I just want to kind of go through this because I don't want you to be confused. I want you to understand what the rules are. All right, let's do a little quiz. We have these two variables. Are they going to have the same type? No. We wrote two different lambda expressions. Even though they're token by token the same, they're two different expressions. You're going to get a separate type every time, so they're going to have different types. What about this? We can, since C++ 20, we can do this now. No? Is it the same type? Yes, because you only wrote one lambda expression. What about this? Is it the same type? Yes, because you only wrote one lambda expression. What about this? Yes. What about that? Same type? No, two different types because you wrote two different lambda expressions. Different types. You're good. Here's a tricky one. This is, again, a new feature we have since, I believe, C++ 20, 17 or 20, I forgot. Template auto. So this is an automatically deduced non-type template parameter. And you're going to say the default value of that is going to be a lambda expression. Are these going to be the same type or not? No. Why not? Sorry? Yes. So it's a template. It's going to be instantiated every time you do that. So it's going to evaluate the lambda expression every time you do that. So it's going to treat it as if it was a new lambda expression. So it's going to generate a new type for you every time. That's really cool. You can use that. This is the next idiom, the unique types generator, which was invented by Chris Yushak. I noticed this on Twitter. I mean, I don't know if he actually invented it, but he posted it on Twitter. This is where I saw it first. So I'm going to credit him with the invention of this pattern. And yeah, so you can do this weird thing where you declare variables one after the other, and it looks like they're the same type, but under the hood, each one of them will have a distinct type, and you don't have to actually write that. So that's really cool. Actually, there were a bunch of replies on this tweet. Denise says, "Oh, this is so cool. I also find an abuse for it." And then Gashper wrote, "I'm going to use that too. That's amazing." And I was like, "Oh yeah, this is really cool, but what are you going to use this for?" Like, and yeah, so apparently there are actually some interesting use cases. So there are, cases where you do want to generate a new type every time. And previously there were like quite ugly techniques for this. There's this underscore counter macro that you can use to like concatenate it onto the end of a type name to make it a different type name every single time. You don't have to do that anymore. Like, this makes it a lot easier. Corentin says, "This is smart. I still don't understand." And then, Corentin gives me another example where this can be really useful. So yeah, this is a cool pattern. And now we're done already with the current standard. And we're going to jump to C++ 23, which is the upcoming standard, which is feature complete now, but not released yet. That's going to happen next year. But we already know that C++ 23 is going to have a cool new feature called Deducing this. And if you have been to the talk that I gave an hour ago in this room, you already know what this is about. If you haven't, I'm going to give you a super quick intro to deducing this. So there is this thing where you can overload based on whether this, like the object itself, is const or non-const or L value or R value, and you can do this by using these const and ref specifiers here. And sometimes you have to write all of these overloads. For example, here, if you implement optional value, depending on whether the optional itself is an L value or an R value, is const or non-const, you need to return a different type from this method, right? So you need to write all of these for overloads, but they're doing the same thing, so you're kind of duplicating the same code over and over again, which is really annoying. And there's, in C++ 20 and before, not really a good solution for this. So either you can write the same code 4 times, or you can have one member which implements the thing, and then the other 3 are referring to it, but then because the return types and arguments don't match, you have to do these ugly casts. It's not great. Or you can factor it out into a private member function. And then that's going to do the thing, and then the other, the 4 like public members the overloads need to refer to that one. But this is also quite verbose, and in C++ 23 we don't have to do that ever again, because we can actually template on the type of this. We can template on the type of the object itself that the member function is being called on. So we can template on whether it's const or non-const, or whether it's ref or ref. And we do it with this new syntax, this self ref. And the self, it doesn't have to be self. We can take it, we can call it type name T as well, but self is just kind of, it's a good name because this is what Python people do. Anyway. There's also, you can use this short syntax here if you don't need to name this type. Same thing. So this is the feature. You can write this type name, and then it's going to deduce automatically for you the type of the object that you're calling this member function on. So that's the new feature at C++23. And one thing that it allows you to do is it allows you to write recursive lambdas, which is really, really, really cool. How do we write recursive lambdas in the pre-C++23 world? Well, it turns out the naive approach doesn't work. Let's do the canonical example. Yes, let's implement the factorial. Like, obviously never actually implement factorial with a recursive function, but it's just a textbook example for recursion, so I'm just going to use that. Let's write factorial as a recursive lambda. Okay, so auto f equals, and then we pass in an integer, and we compute the factorial, and we call the lambda itself recursively. Obviously, that's not going to compile. You can't do that, right? Because you haven't actually finished initializing the f yet, so you can't refer to it inside its own initializer. That's not going to compile. We can cheat. We can make it a std function, f, and then we can capture that f by reference, and then we can refer to it inside the lambda. This works. This compiles. However, it's not great, right? Because std function, it's a type erase type. It has lots of overhead. There's going to be inside, you have type erasure inside. So you have like virtual functions, like indirection. Potentially you have a memory allocation. So this is all runtime overhead that you don't really need. So that's not good either. One thing you can do is you can't basically name the lambda itself in its own body. You can't do that, but you can template on it. Or you can not quite template on, yeah, I guess you can. So what you can do is you can pass the function into itself as a parameter, and then you can template on that. So you can say, okay, my factorial is, I'm going to pass in a function, and I'm going to call that function recursively. And then you just have to basically at the call side pass the function explicitly to itself. And that's going to work, but it looks ugly, right? But with deducing this, instead of passing some function, you can just make the first implicit parameter, which is this function, which is the actual lambda itself. You can make that explicit by using this new syntax, this auto self. And now you know it's going to be the actual lambda itself. And now you can write it beautifully like this. This is the straightforward syntax. You can call it the way everybody expects you to call this. So thanks to deducing this, we get recursive lambdas. You might think, okay, I'm not going to use this in practice, but I recommend you watch Bendin's talk from CPPCon last year, where he talks about deducing this and all the cool things you can do with it. And in that talk, he actually shows kind of a really cool use case. And I want to mention this briefly here as well, because it actually combines two idioms that we have talked about. It combines the lambda overload set, remember the one with overload and then the aggregate, and you just give it like multiple lambdas, you inherit from all of them. And we're going to combine that with the recursive lambda thing that we just saw, and we get some really, really cool stuff. So here's Ben's example. We have a binary tree. This is, again, classic textbook stuff. We have a binary tree, and we want to implement, basically, we want to count how many leaves that tree has. So we do like a classic like binary tree traversal. This is like computer science 101, right? But we're going to implement the tree as a std variant of a leaf and a node. Okay? And now what we can do is we can do this lambda overload set here, which you're already familiar with. And then, because it's a variant, we can implement count leaves as std visit and give it a lambda that it's going to apply on the variant. And that lambda, actually, it's not going to be a lambda, it's going to be an overload of lambdas. So we're using the overload set. And you're going to say, okay, the thing that I want you to call on this tree is, if the tree is a leaf, just return 1, because obviously it's just one leaf. But if it's a node, then recurse into the node and call the overload set on each child node, basically. So this is your tree traversal, and I'm calling the lambda recursively here inside. And you might think, why does this work? I'm not just calling this thing recursively. But it turns out deducing this is really clever. Deducing this, if you do deducing this, this parameter, this const auto self, the type of self is going to be the statically known most derived type, right? It's not going to be the lambda type of this thing. It's going to be whatever the actual type of that object is, which is the overload set, right? This is the most derived class, which is known at compile time. So this visit, this self, is actually going to be the whole overload set. So we're calling the whole thing recursively here. And that's going to do the right thing. That's going to do the tree traversal here. So next time you're applying for a C++ job and the interviewer gives you one of those really boring questions like implement a binary tree traversal, you can really impress them by writing this. And then you're going to get the job. But you need to make sure that you have a cutting-edge compiler. As of right now, the only compiler that's already supporting deducing this is the Microsoft compiler. GCC and Clang don't support it yet. Hopefully, they will support it soon. And these are some fun C++ Lambda idioms that I hope you enjoyed. Thank you very much. And we even have 3.5 minutes left for questions. Any questions? All right. If there's no questions, then thank you for coming to my talk. I hope you enjoyed the conference, and have a good evening. And I'll speak to you outside if you want to stick around and talk a bit more about this. Thank you so much.